my particular pleasure to introduce Dr. Clas Jacobson as a keynote speaker for this morning. Clas is Chief Scientist for the United Technologies Systems and Controls Engineering Organization. And in his role, he works with the UTC business units to ensure capability in systems engineering and controls. Dr. Jacobson received his PhD degree in electrical engineering in 1986 from Rensselaer Polytechnic Institute. He was an associate professor at Northeastern University in Boston until 1995, and since then worked for UTC in various roles. Thanks, Clas.
Thanks. Thank you, Hubertus. Let's see. A couple things, and I'm looking at clocks. Okay, so I have how much time? Until 45 minutes. So I go to roughly 8:15 or 9:15, a little bit more. So a couple things to provide context. So Hilden gave a great talk yesterday. I wish I told him last night that I wish I had gone first. Now I actually have to try to say something that, but I did learn to remove all video and sound. So the idea is to go low tech, right? So want to set the right expectations. The other thing is, and I'll make a couple more comments. I've been sort of with a community like this for a very long time. I was here in 2000. I haven't really been back to this community since, but there were a few people there. There was a younger Hilding, there was a younger me, and there was a Hubertus, and maybe there was probably I remember 20 people in the room or something like that. So I'll talk a little bit about that history in a few minutes. What I want to try to do in the next 45 minutes, and 45 slides, so I'll go very quickly through things. In some ways, I'll skip around a little bit, is to give some view of systems engineering, some view being it's biased. I've worked for 18 years for one company, so that means I have a limited view of life. On systems engineering, so I want to say what that is. I want to say, I could do this backwards or forwards. The last chart is a chart about Modelica to this community, at least my own sort of views about sort of what we could or could not do. So did I do something? Sound is okay. I'm really going to talk about, in some ways, a few limited areas of product development. And what I'm trying to do to this audience, in a way, I could remove Modelica and just have systems engineering opportunities in product development. But there's a few things here. I was here in 2000, so that was 14, 15 years ago that I became aware of this community. And certain things have been really well in terms of Modelica and UTC and various things. Certain things I think are either continued opportunities or missed opportunities, depending on sort of how we view this. So let's see if I can explain these words as we go through. First of all, say thank you, or the right way to read this chart is everything I say that's good is due to something else, and everything that I miscommunicate is due to me. But in particular, Alberto Sangiovanni Vincentelli, who some of you know at Berkeley, helped considerably with this chart, and Kevin Otto, who's here, actually helped considerably with this talk. And we've been doing systems engineering for a long time. There are lots of other people that I could add here, but there's a few people whose thoughts are more strongly represented here than others, and we'd come back to this at the end in terms of questions or comments or complaints about people. So I want to talk about really three things. Systems engineering design flows. So, where are we in terms of this? Hilding had alluded, and maybe there's several people in the audience that already know much more about this than I do, but there are classic ways to think about design processes or design flows. And there's a kind of simple way to think about this of what was done sort of in the 1960s in various situations. And it basically doesn't work today. So I'll try to explain in some sense why, or give you a couple examples. Then there's a positioning here. I'll jump around a little bit, but I'd say languages for design. So Modelica is one of many. It has some strong features, in my view or our view, whoever I'm speaking for, that enable certain things to happen. The words there are proper semantics or clear or defined semantics. There are some things that are interesting. I'll make a few short comments about this. This is really not a talk so much about Modelica as it is about Modelica in the placement of something else, design flows. And then I'll give a couple of examples where I actually think that the opportunities for Modelica are broader they're near. I had a discussion yesterday. I'm looking out in the audience here. I can't sort of locate people, but Marc Frouin from Dassault and I, so I think these are interesting sort of areas where you can exploit the language at this stage. 14 or 15 years into the program. Maybe arguably we're a little bit beyond where we should be in terms of utilizing the technology. Okay, so the key points I want you to walk away with. I think this is the last chart of my talk, and maybe the goal is to try to explain this quickly in the next few charts. So Modelica is a good tool. It does things that we have actually found to be useful. I would say physics capture and reuse, and I'll say a couple of words about that and give you some graphics and go quickly charging through that. But I really want to talk about Modelica in the context of what systems engineering or things, which is a longer topic, which means very different things to very different people. So there's different cultures or subcultures. There are things that, particularly at UTC, which again is the only thing I can really talk about because I've been there, although it's a pretty interesting, broad company. I'll mention what it is later. It's really about things that are changing due to really one or two things, depending on how you count. Complexity or software. I don't like the word complexity, so I defined it. It means sort of three things to me: heterogeneity, dynamics, and uncertainty. And the John Doyle definition, he's a professor at Caltech, says that complexity means really two things: interconnected systems and uncertain systems. But depends on sort of what it is. But you can begin to see why Modelica is a good tool in this case, because it handles heterogeneity, it handles dynamics, maybe not uncertainty, not yet. Systems engineering means a few things. I'll say this in the middle, particularly as a definition that pertains to me. And then what I want to do is get to a couple examples where Modelica has opportunities, or something like Modelica, in a few different places. And I could use lots of different examples, but I want to pivot around two, which is getting things right up front and getting things right at the back end of product development. And I have different sort of views, and I'll go through this in a minute or two, of what product development is. So, so just quickly, a tour of history. So I was here in 2000. And we had a small meeting, and Carl was there, and Hubertus was there. I think Hubertus was still a graduate student. I don't think he had graduated yet, whereas he fled somewhere. There he is. And we were enthused with this. We were working on fuel cells at that point in time at UTC, or at least I was. We hired Hubertus. We hired Jonas. They came to the United States and became a Red Sox fan. To his continuing sort of frustration, although recently it's been better. And this was actually very powerful. It was good. So here's sort of a systems view, a cartoon of sorts, that really talked about why Modelica was good. So you had I got to figure out which way I'm pointing, but there's lots of different subsystems, lots of different blocks, lots of different physics. So we actually modeled from fuel in, which was natural gas, to electric power out, the entire system level description, and we used that for controls. So we did multidisciplinary, multi-physics, multi-scale, we did species, and it was a pretty exciting way to capture physics. It was very easily deployed to a very wide range of people through the Dymola tool suite. We had component reuse, we had drag and drop. This is a build, but let's go through it quickly. We built libraries. We built our own libraries. We built it off of Hubertus's base classes that he used in his graduate days, which have turned into sort of the public versions of libraries. And this was largely very positive. We were able to put things together very quickly. There's a separate sort of discussion to this. This is not this talk, but I could give another talk. In some ways, the quip about this, which doesn't really come completely into this talk, is that we were able to build rapidly systems that we weren't able to understand. So reuse was a very good thing, but then the systems became so heterogeneous. So we went off. There are some other friends of mine, and I'll mention this. We started a sub-theme within some government funding to actually figure out how you actually can look at these kinds of systems and understand and tear them and break them into pieces. But overall, this was a very positive experience. UTC changed a little bit. So I was going to do this first. I gave this talk to a lot of people, and people gave me a lot of advice yesterday or the day before, and then I decided to ignore it and say, okay, well, this is my talk, I'm going to go give it. But I could have talked about UTC first, but I went through the history. UTC, for those of you who don't know about it, it's a moderately sized company, medium-sized company. It's really half and half. It's in commercial. John Burns, several people are traveling with me here, says, you really don't know what a UTC is, and that's fine. But our individual brands you've probably heard of. So on the aerospace side, we are Pratt & Whitney. We make gas turbine engines for aircraft. We make helicopters. That is an S-92. That's a commercial helicopter. You also see us with Blackhawks and other kinds of defense-related items around the world. We are also UTC Aerospace Systems, which is a fairly large business unit by itself. We make environmental control systems. We make electric power generation and distribution systems. Basically, we make everything on the airframe at UTC past the airframe and avionics. On the commercial side, we're sort of the same. We make everything in the building basically past the envelope and lighting. So we do elevators and escalators, and then we have a business unit called Climate Controls and Security. This is all new, about a year, so I have to slow down and think about this. It's the carrier business, and it's a fire and security business. It's the old Chubb business. It's the old Kitty business, and this has all been acquired and merged and moved and rearranged since about 2004. So we are not really a U.S. company. We do about 40% of the sales in the United States. We do about 25% of our sales in Europe. And we are about half and half. So if you think about us as aerospace, we're not. We're actually more commercial. We're more carrier air conditioning a little bit than we are gas turbine engines. We deal with a lot of businesses, both in terms of aftermarket and manufacturing. So we have pretty broad range. When you think about Modelica, or I stand up here as Modelica, this is the kind of opportunities that I see in front of me. And we do interesting things. So I got to watch time because this is a chart I could spend a lot of time on. They sort of buff the company kind of thing. But a different way to think about this is, where, particularly if you're sitting in a Modelica audience, where does this actually come into play? So these are 4 products. I won't talk about them in detail or talk about the problems. I'll talk about one in detail going through the rest of the talk. Up here we have the 787, which is the new Boeing airplane. Let's talk about that one and then briefly talk about the others because I'll spend some time on that in the rest of the talk. So this is a quote-unquote more electric aircraft. We'll talk about what that means a little bit later, but from a commercial perspective, this aircraft compared to comparable aircraft in its size range is 30% more efficient. Years ago, those of you who may have gotten here by plane, energy was effectively zero cost. Other cost structures affected the aircraft industry. Today, about 60% of the operating cost of a airline is fuel. And so if your plane is 30% more efficient, you're gonna have a competitive edge. And this is really due to 2 things. It's more electric, it's also composite, so it's lower weight. The rest of these, just to walk around, we'll come back and talk about the 787 and perhaps what it means relative to Modelica and product development. Just hit a few of these. The Cooltech system, so we do a lot of air conditioning. Chlorofluorocarbons are not so good for the environment. We supply a lot of refrigerants in various ways. So market pressures, so just like the 787 market pressures on fuel efficiency, here market pressures pushed us, or regulations, particularly in Europe, moved us to actually consider different refrigerants. So this uses CO2 as a refrigerant. Several people in the audience have done this in terms of modeling and looking at this within the Modelica community. So these are refrigeration units that use CO2. If you haven't heard this, it may seem weird that CO2 is a greenhouse gas and you're using CO2 as a refrigerant, but you're not adding anything more. Fluorocarbons have a multiplier effect, and so the global warming potential of CO2 is 1, and the global warming potential of fluorocarbons is around 10,000. So this is actually a good thing. It's very complicated to actually engineer this. So CO2 is a fluid, and there are people here from UTC that worked on this. Is a little different. It operates largely in a transcritical region, so it's a little different as a refrigerant, and pressures are a little bit higher than in other cases, so there are engineering challenges. The bottom one is the world's fastest helicopter. It is a new helicopter from Sikorsky, and the one on the bottom over here is the Joint Strike Fighter. We supply the engine, largely the propulsion system. It's a combined propulsion and guidance system, so it uses ducted fans and fans to move, so it can do vertical takeoff lift. And so the takeaway in some sense from these, although I'm flashing a chart about products, is that there's much more integration of these systems, whatever that really means. There's definitely more software. So functionality is being provided by software, which is both good and bad. I mean, iPhones are fun. Software and safety critical systems might not be so fun, but we can talk about that. And there's many more operating modes for these kinds of systems that are available largely because of, in many ways, software. So how do you engineer these systems? Okay, so this is not a tutorial in product development, although we'll sort of rapidly blow through some stuff to make a point. So, years ago, stage gates became sort of the fetish of industry, in a way to sort of move from one gate to another. So you do something with markets or understanding, you do preliminary investigation, you do some more detailed investigation, you build a business case, you do development, which may involve some kind of technology development or maturation, technology readiness levels or things like that. You do testing and validation, and then you release it, and after you release it, actually, there's probably another gate where you sort of come back and look at post-certification engineering or sort of other things in the field. And at each of the stages, you have a review. And at UTC, this is done pretty much by the president of the business unit for large programs. And you say, how are things doing from a business perspective and a technology perspective, and are the projects actually working? And in some sense, the cartoon of this is that you're trying to drive down risk. So I had sort of an email debate over the last few days about sort of how to present this. And I'd say that, from my perspective, systems engineering is all about risk. And it's about risk control, risk reduction. And none of what I say is actually due to me. So that's an interesting thing. John Holding, who was up until recently effectively the CTO, I don't remember what his title is. I think it's Executive Vice President of Product Development for Bombardier. Said effectively the same thing. He said, systems engineering is about risk control or risk management. And what all the stage gates are is to understand and drive this down. There are other ways to think about this. If you're, think about systems engineering this way, how much degrees of freedom do you have? When you're sort of looking at prototypes and you're looking at conceptual design, you have large degrees of freedom. And when you're actually building the product, you want to have 0 degrees of freedom. And Hilding alluded to this, so it makes me think that maybe this has penetrated part of this community about design V's. He showed sort of, the red path through that. I hadn't quite heard that. Red's a bad color. Maybe the green path might have been better, but red means something to me differently. But there's this canonical view of systems engineering. So you start at the top, you go down to design V, you decrease length and time scales in some sense, you go through and you design components, and then you do verification, you do subsystem integration, system integration, acceptance testing, and you release a product. So we could talk, and we should, where are things like Modelica, where are design languages, where do they appear in this? And where is modeling and analysis appear in this? And, it appears everywhere. And it has different uses. So what's not really shown on a chart like this, and in some ways not done. So this chart, at least I'm a partial student of history. This largely came about in the NASA efforts around 1960 or so. There's a NASA handbook, I think dated, there's 2 versions of it, 70 and 82 or something like that. So they wrote this down. And, it's not really shown here are the gates. So what analysis do you do at what points in time so that you have a linear flow? So you go back, and then you don't come back. Okay, because this time scale at the bottom could be fairly large. So let's think about this. That was done in 1960. Today is 2014. Some things have changed. We have smarter phones. Mine's Nokia, which now sort of belongs to Microsoft, which might be smarter than somebody else, including Linux, but we have different issues, maybe software. So here's a different picture, public. Everything I say here is public. Somebody said, this is approved for public release, so I'm sort of up against an edge of what I should or could or can say. But more electric aircraft, what's happening here is just a schematic. Things are becoming sort of more distributed, and I'd be glad to talk later what more electric really means. But here's a graphic next, if you've never heard about this, to sort of get your attention. So electric power generation and distribution is actually a very simple problem. You go from source to sink. You plug something in the wall, you get electric power. You have generators, you have loads. So the 767 is the single line drawing. The architectural picture of this is up there. And this is a public view. This is a Honeywell patent. You can Google this. It has nothing to do with UTC. But this is what sort of more electric architecture looks like. It's meant to get your attention and say, wow, that's more complicated. Why is it more complicated? So I grew up and I was a controls person, and nobody wants to see the controls person arrive on a program. Trust me, I've been there, done this for 18 years. We do sensors, we do actuators, we do mathematics. Sensors break, actuators break. Nobody understands mathematics. You don't want to see a controls person. Okay, nobody wants to do that. They didn't wake up some morning and say, gee, let's design a more complicated electric power generation industry. So why does it look that way? Still have the thing, you have sources at the top, you have sinks at the bottom. So what's going on, essentially? I mean, there's a lot going on here. I'll say this 2 or 3 times if I get through the slides. When you have a more electric aircraft, it depends on the electric power for operation. So you lose the electric power on a 767, it is so-called level A critical. It's catastrophic loss of life. It means it goes down. It doesn't come back up. So what this basically is trying to get to so-called reliability or availability. So you have sources and sinks. In the middle, it's hard to see, and I don't have a pointer that can go through this, or at least I don't think I do. I'm not going to stop. But there's so-called a ring bus at the top, and you have many ways of going from source to sink. In fact, you have 2 to the n ways, 2 because you have a contactor. It's on or it's off. And n is a very large number. And it's all controlled by a distributed software system. So how do you know if it works? But when it works, it should be much better. Okay, here's what happens in practice as a cartoon. So that's a 787 in flight test out in Washington. It rains in Washington, so you'll see people are sort of looking at rain. It's a miserable place in the world, sort of great coffee, but lots of rain. This is a cartoon, publicly available picture of a test facility in Illinois in the middle of the country at the bottom. It is called ABSIF. You got to be very careful when things have acronyms, especially 3-letter acronyms. It means that bad things are happening. But this is ABSIF, Aircraft Power System Integration Facility. We should talk about what power means. On the 767, it was roughly 300 megawatts of power. The 787, the smallest version, is 1.6 megawatts of power. That facility does things like lightning tests. It's a pretty exciting facility to be in. It's very expensive to run. I tell people, I used to teach, I spent 9 years teaching. And I say, you should take people, if they ever have the opportunity to do this out there, and you say, these kinds of facilities really, shouldn't really be built. If you could do something else, virtual engineering, modeling, something else, because these things are very expensive, because it's not just the facility, it's all the people that run it, it's all the safety, it's all the regulations. This is something you never see in academia. Okay, and here's the cartoon of things that go wrong, or begin to go wrong. So you come down a design V, you go up a design V, and you go over. And you go broad because testing is incredibly expensive. And you go up, and you come back, and you do even more testing. Why is that? Because this system has a lot of modes. You used to be able to certify a 767 by basically going through and testing every single path. Might not be quite possible anymore. Okay, here's a chart that Alberto gave me, San Giovanni Vincentelli, and it's a cartoon, but it's interesting for those of you, and I don't play at all in the automotive market, people do here, so they can say whether this is correct or not, but this was a chart at least generally available, or publicly available from General Motors. Now what's interesting here is that used to be a mechanical system. I grew up and there were carburetors. That's how old I am. Now you have other things, but the electronics is actually shifting to be much more important. And so it's not just UTC that's facing this challenge. And lines of code is a bad metric. It doesn't really tell you about complexity, but it's a surrogate in some ways. And the growth of software and number of processors on cars is pretty amazing, but it doesn't tell you that you're complex. Remember, I hated the word complex in some sense. It means heterogeneity, it means uncertainty, it means dynamics. But software tends to sort of mean that because it's a surrogate. You're getting much more heterogeneity of connectivity, you're getting much more dynamics. Software is changing very rapidly. Usually timescales of electronics is fast. And you have a lot of uncertainty. It's able to cope with the environment much more than it is. So that's good, but it makes it, by definition, complex. So people realize this in, 2009? Much vaunted agency in the United States. There are people here who can speak about this much better than I can. Started a program called Meta to move away from the design V around sort of three things I put in yellow boxes. It was a pretty aggressive or ambitious program that had some success. It definitely got people's attention. And there were issues up here in validation and verification, V&V. There were issues about flexibility of the design. How do you actually do a design and architecture that allows you to reconfigure it over time or adaptable over time? And how do you actually flow down requirements that are taking into account different metrics? So these were historically, when NASA did this, size, weight, and power, but there are other metrics that actually talk about complexity. So for those of you who don't know about this, it was sort of a useful event. The broad agency announcement, the call for proposals is still worth reading. There was a lot of interesting history in there and about why things don't work. And the National Academy followed this. If you're sort of interested in history or why this is, and you just don't want to listen to me and talk about UTC and see what's coming next, this is actually an interesting report. It's a letter report. It was never followed by a formal report, and most of these charts I'll make available so Hubertus and Martin can sort of post it and you can see this later. But it's interesting, this is a word chart for sure. But we talked about engineering risk in large systems. So those are the kinds of systems that I care about. We talked about software quality assurance and talked about requirements related risk. So I'll come back to this in some sense. A very interesting report to read. Was, I think, spot on. You could argue that it's as relevant today as it was when it was written. So what do people do today? Most people don't use Modelica. 400 people in the room, maybe a few others beyond this, relatively small community. Computational engineering, still not widely dispersed in industry. So it's like going to the grocery store, right? You go there, you forget, you make a laundry list, you make a checklist. Okay, so they call it something different, but these are checklists. And the checklists for the electric power generation and distribution system for a commercial aircraft, it's a stack of paper about this big. Those are the manuals that tell you what you actually have to deliver. They don't tell you how to deliver it, they tell you what you have to check off, and there are standards, and you work in the industry and you roll these things off your tongue. So you have 4754A, which is a standard, you have Mil Standard 489, which has been retired, you have DO 178B for software, you have DO 254 for hardware, and you know all these acronyms and they're checklists. They're useful. They do help, they do protect, but they're definitely cumbersome and expensive to satisfy. And there's a lot of testing involved, and there must be, but there's also a lot of subsystem testing, which is pretty complicated, or unnecessary perhaps, if you are able to do more modeling and computation. Okay, so part one's done. let's go through part 2 quickly and then get to some areas of opportunity that I think are unrealized relative to Modelica. And I've already given some hints and clues so I can go fast or faster than I'm already going. So, there's several of these buff the company slides. So UTC, so I changed jobs a couple of years ago. We formed a new group called Systems and Controls Engineering, centralized at UTC. Hubertus read off sort of what I do. It's interesting listening to all that. Work with the business units. There's something in here I should read. Ensure capability in systems engineering. Yeah, I wish I was doing that. But systems engineering actually means 4 things. And we defined this. We haven't often thought about this fairly carefully. Some of this may not be that on the tip of your tongue, or you may not have heard this before, and so maybe this is just sensitizing to what people care about. Requirements. So getting requirements right, and I would say, relative to this chart, it's analysis of requirements. And I'll talk about that. Some other industry people are here, and there are tools and there are things you can buy to capture requirements, but there are not necessarily tools and methods to analyze requirements. We'll talk about what that means in a few minutes. Architectures. There are physical architectures, functional architectures, control architectures, network architectures, there's a few others. If you don't get the architecture right, you will pay for it forever. And so, in our business, we don't build one product, we build families of products, and our products stay in operation for 50 years. So we have to pay attention to architectures a lot. Model-based analytical tools. So this is where you see things like Modelica coming in. This means the code in this is replace test with models all throughout the process. And then design processes. So the design V doesn't work. What does? Or it doesn't work for me. Okay, so what does work? So different picture of design processes. There's a lot in code, as there usually is, in charts. A lot of this is due to Alberto Sangiovanni Vincentelli. So he came up with this notion, which is called platform-based design. It replaces a design V, or it modifies a design V a little bit, and it does it in 2 or 3 different ways that are subtle but critical. So you separate requirements from architecture. So you satisfy what you want the system to do, as opposed to how you're actually going to satisfy those requirements. And this is called orthogonalization. A lot of times people sort of keep these together, and so it becomes very commingled as to sort of, what is it we thought we were building, and how did we actually do the architecture? So there's validation and verification, and then you bring this together and you do analysis. And those are the tools. That's what people should go buy from someone. So you want to capture the requirements formally, you want to capture the requirements formally, they could be different semantics, you want to bring them together, you want to do some analysis, and you want to say that's good. And you want to do this in a way where it's incremental. So you want to bring this virtually forward in time so that you're not seeing that spread like I showed for aircraft testing, where things take a lot of time for test and then you got to loop back. So basically what you're trying to do is bring the platform abstractions and the tests earlier in time, and you want to do these mini Vs each stage of the way through. So the takeaway from this is, if you don't like the design V, which I don't, then you should modify it. It's not bad, it worked. It worked, just incidentally as a historical artifact, it worked and it still works where you can do testing. 767, that was simple, you can test. So NASA developed this. You'd think that the Apollo program was a little more complex. There was something like 450 full-scale tests of the engines. They had a combustion instability. They tested their way out of it. So if you can spend a lot of money and time, you have infinite money and time, use a design V. If you don't, use something else. Government's a great place. So a little interlude in code about Modelica, but so you need languages at those stages. You need to capture the requirements, you need to capture the architecture, and you need to do it expressively enough that you can do analysis. You need to have a mathematical representation that you can reason about the system in this sense. So, what does that mean? Modeling languages really are expressing designs. And there's lots of design tasks that you should have here. There are lots of languages that exist. And at least you can think about this as three things. You want it to be easy to use. Not everybody in life has a PhD. Not everybody in life sort of is available. You want this to be sort of easy, scalable. It's not so much the PhD issue. It's that, does everybody sort of have to focus on all the details for everything? The answer should be no. Formality. You need to have enough representation, and I would say mathematics here, to be able to carry out analysis. So there's a mixture here, and this is the takeaway. If there's one thing that I can sort of pre-shadow in the next 10 minutes of this talk to finish, that's where Modelica should shine. That's where the gap is. Came here in 2000. There's not been a huge amount of work done on the formality or the exploitation of formality. So we invest in our own tools. I don't do that. We're not a tool business. We develop products. We don't develop tools. When I'm spending money on tools, that's probably not a good thing. Expressivity. So you want to capture a wide range of things. You could have a language and a formality that does one thing, but if it doesn't do a few more, then it's probably not as good as it needs to be. Okay, ease of use. So this is domain-specific languages, domain specificity. This was, there are other domains that use languages, VHDL, Verilog, whatever. That's a good thing to go look at historically, and also what your nearest neighbors are doing, because these tools actually increase and decrease ranges of abstractions or levels of abstraction pretty effectively. That's how people actually get away with designing much more complicated systems on chips today, as opposed to what they did years ago. Formality. So now you have to decide what it is you want basically the analysis to do, and then work backwards. You shouldn't go forwards and say, oh, I have a language, what do I do with it? So finite state machine semantics and stateflow or things like that enable other kinds of analysis steps, and I'll talk about this in a few minutes rather than on this chart. And then expressivity. You can have very general things, but in some ways they're too general. So these things are a tripod, and they rotate in some things a little bit unbalanced all the time to get to something that works. Okay. The big thing here is to use a design language. Just because you have a design language, and you can express a design, the only real purpose of that is documentation, which is a useful purpose. Not a lot of things are documented, and part of safety critical systems is to do traceability and to document things all the way around. So if you have a design language, that's useful, but it's much more useful to be able to do something with this. So you want executable requirements. Simulation is the first thing people go to. So as a personal talk, you stand up here and you give a keynote. You shouldn't be talking about a specific technical result, and you should be giving a broad thing, but you're always one person standing up here. I've never actually found a time domain simulation to be other than a feel-good panacea. I know I'm being videotaped, so I'm being recorded, so somebody will come back. But you have to have something executable. So maybe I'm saying, okay, if I didn't find that to be useful, what do I find to be useful? So other aspects, scalability, speed of execution. Now you have this issue, MOC, model of computation. This is sort of a Berkeleyite term, but what model of computation are you using? That actually then pivots or says what kind of formal methods you can apply: verification, synthesis, fast simulation, etc. And then we get into sort of religious arguments, or beginning to sort of where we get up against a border. This is a good meeting or culture to begin sort of talking about this: Simulink versus Modelica, Mathematica versus other things. There are strong pros for Modelica that are not in other places, and in particular, Modelica's semantics are precisely defined. But are we using it? And the community, if you will, the health of that in many ways, or a metric, is what's the tool vendor and supply around the language. So go over to MathWorks, you go up to their website, you can find a few dozen or 100 or 1,000 toolboxes. You go over to Modelica. Okay, so let's talk about what could be there. What can you do if you have proper semantics? So, formality. So, there's several tens of thousands of requirements for an electric power generation and distribution system. It's not really, mortals are not there. You know, psychologists determined that human beings can understand 7 things, right? Tens of thousands. So what that means, what does that mean? It means that you have English language. So here's a chart from a program. So this is actually hidden at the bottom. So I'll do a plug again for UTC, or actually IBM omits here with a few other people. So a few of us after the Meta program decided that made a lot of sense, but maybe we should do it ourselves. So we went off and created a consortium, IBM, UTC, Berkeley, Caltech. And we worry about things like this for systems engineering. And one of the things we worry about is how do you actually structure requirements? So we have English language on the other side. I don't expect you to understand necessarily this because it came out of a public study of electric power generation systems. But somebody writes down in English language, you know, no AC bus shall be simultaneously powered by more than one AC source. Is that clear? Not clear? Ambiguous? You then want to move that over. And I was talking to someone yesterday. You know, so a lot of this is about reasoning and what kind of reasoning you need to do. So here in this is Lund, Shanghai Jiaotong ranking. This is in the top 100 somewhere. It bounces around a little bit as do everything, but it's a good university, very good university. A lot of things get taught, you know, physics, mathematics, chemistry, all the usual things. How many people actually took a course in the 4 years at a place like Lund in linear temporal logic? I was with someone and they said, you know, if you actually can't read linear temporal logic today, you ain't doing systems. That was Richard Murray, who used to be dean at Caltech. And so he said that in a UTC meeting. So it was kind of like, you know, in our eyes, we weren't having enough education. But, you know, what does this mean? If you look at requirements issues, there's a lot of problems. Ambiguity, non-determinism, inconsistency, realizability, completeness, blah, blah, blah. So there are actually courses and people think about this. And this is more or less an open research topic in some ways. Requirements are informally defined and they're captured in tools like doors or various other tools. IBM supplies doors, but they're not formally defined in a way that's open for analysis. So let's go back to our friend. What does this mean? Well, more electric systems. Nominal behavior, so just to capture this, nominal behavior is not really a problem. Humans can actually understand nominal behavior. There are many things that, you know, when you get into these kinds of industrial realms, regardless of sort of what is infrastructure, you know, there are things that probably people shouldn't really know that much about. But when you get on a plane today, not all the equipment is working. And what's actually flying is called an MEL, a minimal equipment list. And basically you have to fly with at least, or not least, you have to fly with 2 faults out. And that is 3 to 4 orders of magnitude more in requirements than you have with nominal operation. So this is where the complexity comes in. And it's safety critical. So when you have a software system, you can enable safety critical operation. And now you have many more modes. Okay, so this is our friend platform-based design. And when you look at how design is done, a slightly different picture here. You have some agreed to requirements, you have derived requirements, you derive them again, you go to software. And now the question is, early in the process, you want to say, okay, I have a requirement, I have an architecture, I'm going to go build something, is it going to work? If you do a simulation of this, you actually do what's, you know, you actually hit a target. You say, okay, does it actually work? You know, there's an engineering insight. Simulation is not completely useless, but you sort of go and you look. Now the question is, in all those degrees of freedom, is the system going to satisfy the requirements under all possible considerations? Okay, that's model checking. Model checking today works on finite state machines, linear temporal logic. You capture the system, you capture and model the requirement, you bring it together, you say yes, it's satisfied under all conditions, or no, you get at least one constructive case. For the Modelica community, you know, we do a lot of continuous time dynamics or hybrid dynamics. There's signal temporal logic, fairly mature technology. We could do this here. You could exploit the fact that you've captured the system. Remember at the beginning, Modelica is a good tool. Capturing physics, reuse. There's more that could be done. One other example, and I'm done. A big example. So one example, really big, done quickly. This is like Dr. Seuss. So there's a big area. So requirements checking in some ways is really good at the front end. So at the upper part of the design V, have you defined what you want, and are you doing some model checking and making sure you're verifying that? You can do it at the back end, but the system becomes very complicated. Implementation tends to grow in complexity. The other thing you can do at the back end is you can capture, so it's effort, but you can capture probabilistic descriptions of systems. So this is a process. Six Sigma was popularized in the 80s, roughly, Motorola, GE, a bunch of companies. I'd say it's mature. Design for Six Sigma is to turn this around, and you have a flow. So if you want to know this, again, this is a little bit of a editorial comment. How many universities teach this? How many people know this from academia? This is sort of the price of admission for quality in industry today. Maybe a gap. Maybe your universities are better than the ones I hang out with. Let's talk about one particular element of this, because I'm over time. So there's a lot of issues here. So what you're trying to capture here is uncertainty. So you can think about design for Six Sigma as statistical engineering. Kevin Otto gave me this chart. I've used it for years. It's probably 10 years old by now. And really you look at three different flows. So when you look at something like Modelica, what are you capturing? You're looking at flows through the system of energy, mass, and information. And they interact. And that's the heterogeneity part of what I said is a complex system all the way back on chart 1. This is an eye chart, but what you really try to do then is if you can look at these flows and you capture them with some kind of probabilistic description, the idea is what's sensitive to what. So if you have a system and it's very multi-physics, you have electrical systems, mechanical systems, chemical systems, whatever, what's interacting? This goes under the acronym CPM, Critical Parameter Management. And critical parameter management should take the model, should take the parameters that go into it in a statistical sense, and produce some kind of a chart that says there's a few parameters that matter a lot. So this is classic sort of tornado chart. And there's a lot of things that don't matter at all. And you should watch those ones that matter a lot. And you should use them at design to set margins, and you should track them all the way through, mean and variance, through the system. So this is a big study. I sanitized it. I blocked off all the numbers. It means nothing. But what it does is that when you do your initial system, you're going to fail. That's the design V thing. When you go through this, you're going to fail. Assume you're going to fail. Because you have ranges of things. Not everything is nominal. What you want to do is you want to identify what's critical, and then you want to adjust those critical features. So the trick in this, and the theme of what I talked about, and now I'm done, is if you don't like the design V, mash it up. Platform-based design moves it early. Something like model checking does analytics. Model checking is useful for the Modelica community because it's based on formal semantics. If you don't like your statistical answer, go to a design W. So assume you're going to fail, but only come back up once and do it faster. So adjust your parameters and then use those parameters to nail your design. It's important for the Modelica community because if you include statistical variations in those parameters, now you have a platform to actually carry this out. Neither of those tools are available today. Okay, 2 charts on key points. Design flows matter a lot. Cost, schedule. Not probably as in front of people's faces in the Modelica community as I think it should be, so that's the keynote to put it up here. Systems engineering is all about risk management. Drive it down. Cost-wise, drive it down with models. Systems engineering, analytical systems engineering is 4 things. We talked about requirements a little bit. I didn't talk about architectures. That's a different lecture for a different day. We didn't talk wholly about model-based development except around requirements and statistical engineering. We talked a little bit about design flows. Platform-based design, design Ws, other kinds of things. The real issue here, and this is important for this community, I think, is that you get here by formalization of design, i.e. mathematics. You enable reasoning about your system, which is analysis. It's that bringing it together at the bottom piece. Computational engineering today is the ticket to play. 10 years ago in industry, lean was the ticket to play. For this community, final chart. We're using this. 14 years ago we started. It's used in all the business units in some way. It's a good tool. Physics capture, dynamic simulation, use in an overall design methodology and tool chain to varying degrees of use, maturity, it's there. Modelica needs to be more than a dynamic simulation environment if it's going to become a standard. Steady state, optimization, statistical engineering, design for Six Sigma, model checking, these are really areas of opportunity. I'm kind of stunned a little bit. 14 years later, we're not there. And you should look at your nearest neighbors, right? The MathWorks and other places, I mean, this is where the value is. You've got to drive down risk. You need the tools. You don't necessarily need only the platform. I know I heard Martin say this, but from a personal bias perspective, you need some type of interoperability. So it can't be that when you use Modelica standard code on platform A and platform B and whatever, it can't give different results. That supply chain just ain't going to work. Is not. How quickly can it happen? That's a pacing element. The big thing to me, though, is tools. I've said this now. It has much more potential than just a language for simulation. Hilding got into this a little bit yesterday in code. He said, this is a language for architecture capture. I was thrilled, and then we went off and talked about shape optimization or topology optimization. So Germans talk about topology optimization. In the United States, we say shape optimization. But what he was talking about was absolutely correct yesterday. And so, that was hard to follow because he already said what my main point was, and it just took me sort of 55 minutes to say it, that you need tools.